Okay, so we are now recording, and let's take a look at this piecewise function, okay? So we've got a function that's defined as the line 2x minus 1 when x is not equal to 3, and then it's defined as 6 when x is equal to 3. So there's going to be a little jump there, right? There'll be a hole that will jump up to 6, because if we were to sub in 3, we'd get 2 times 3, which is 6 minus 1 is 5, okay? So do we know the answer to the limit as x goes to 3 intuitively? What's our answer? 5. Okay, we know it intuitively, right? We can just say, well, from the left and right, the limit's going to be 5. So despite the fact that the function is 6 at that point, we have an answer, okay? But to be more precise, and which was what he's talking about in the video, right? To give a better definition of this word approaches, we're going to ask this question. How close does x have to be to 3? Okay, so how close does x have to be to 3 so that f of x differs by wait a second, I'm not getting that right. Differs from 5 by less than, and then I'm going to put a little blank there, and that's the epsilon. We're going to do it with a specific example to start, so I'm going to put 0.1 in that blank, but I want you to just put a little note that that's the Greek letter epsilon that we're referring to in the definition. So let's reread it. How close does x have to be to 3 so that f of x differs from 5 by less than 0.1? And we'll kind of outline what that's going to look like in a proof. Okay, so let's talk about the distance from x to 3. What would that be? What mathematical expression gives us that? Yeah, absolute value x minus 3. Good. So in this case, in the real like general case, it's like this. The limit as x goes to a of f of x equals L. That's what we're trying to show. And in this case, a is 3. Okay, so put a note over on the side, right? A is 3. So similarly, the distance from f of x to 5 is the absolute value of f of x minus 5. So just keep in mind that if we were doing this in general instead of specifically, let me put those details off to the side. This would be x minus a, and this would be f of x minus L. So are we following the connection? In our specific example, we're proposing that the limit is 5, okay? And that the point we're approaching is 3. So we're kind of trying to make a comparison between our specific example and the general case. And here again, our specific example and the general case. Any questions yet? Okay, so with that, we seek to find a delta such that the distance between f of x and 5 is less than 0.1 if the distance between x and 3 is less than delta. So our goal is to find the delta that satisfies that. Remember, this 0.1 is really the epsilon that we just happen to be choosing in this case, right? Okay, so here's how we're going to write up the proof.
Which we always do. The epsilon, we just choose the epsilon, right?
The epsilon, right, is our choice, and then the delta is going to be dependent on the epsilon. So really what we're finding is we're finding a relationship between epsilon and delta. Okay? All right, so let's start with where we're headed, and we'll see if we can back up to the answer and then build the proof from there. Okay? So here's how we're going to start. We're going to say this fact is what we're trying to show, and we're going to unravel that to get to the beginning of the proof. Okay? So instead of writing it like that, I'm going to write it as 2x minus 1 minus 5 is less than 0.1, because that's what f of x is. And then we'll clean that up. 2x minus 6 is less than 0.1. So what I'm doing right now is I'm backing up so that it looks like the absolute value of x minus 3. So I'm going to pull out a 2 and then divide both sides by 2. And I'm not going to simplify that. I'm going to write it like that. I'm going to write it as the absolute value of x minus 3 is less than 0.1 divided by 2. Well, look at the form that this takes. Look at the comparison here. We just saw that means that if we choose delta to be 0.05, okay, so delta therefore is 0.05, then the condition is satisfied, right? In other words, when epsilon is chosen as 0.1, we just showed you this proof that delta would need to be 0.05. But it's not fair to start a proof with the end in mind. What we have to do is really build it from this statement. So now that we have this relationship, we can do that. So we now know that delta simply equals epsilon over 2. That was the key I've been hinting at all this time. We need a relationship between epsilon and delta. And then we would build the proof. We would actually build the proof from scratch. So we would say, okay, starting with this premise, x minus 3 is less than delta. Now that we know what the relationship is between epsilon and delta, I can say this. And then it's just easy algebra backing up into our general statement of having epsilon on the right. So we would say 2 times absolute value, bring the 2 in. This, I know it kind of seems like hand waving, like all a bunch of artificial work, but this is like the easiest example that's always shown in order to just hint at the idea of epsilon deltas. And then, so then this is 2x minus 1 minus 5. And there we have our conclusion. Okay, so by doing this work, which by the way, we use the specific epsilon. If we change the epsilon, that would change the delta, right? If we change the epsilon to be 0.01, the delta would be 0.005. So it's this idea that whatever epsilon you pick, you'll be able to derive a delta. And this thing proves that. That statement proves that. All right, questions that I will try and answer, but I've never taught real analysis, so don't be mad if I can't answer. Go ahead, Hamza.
So the delta equals epsilon relationship, that changes with each value?
Exactly. The epsilon and delta relationship changes depending on the function. Okay, it changes depending on the function.
Does it change on the function or the value?
I believe the function. Yeah, it's going to change depending on the function. Yeah.
So, to me, it just like the proof just sounds like you're taking the word approaches and then just assigning math values to it. Like,
Yes.
It's not particularly convincing.
Yes.
Like, it's still kind of hand-wavy.
It is still kind of hand wavy.
Like,
I agree. That's where I think a study of real analysis, which I took a course in it in undergrad and I just don't remember anything about it. Although I probably have the files from the course. Here's the formal definition that goes for single variable, and that'll help you understand the multivariable a little bit. So here's how it starts. Let f be a function defined on some open interval that contains the number a, except possibly at a itself. Then we say that the limit of f of x as x goes to a equals L if, here it is, for every epsilon greater than 0, there exists a delta greater than 0 such that if 0 is less than x minus a, which is less than delta, then f of x minus L is less than epsilon. Okay, so we're going to write that in a couple of other ways, and then we're going to draw a picture that sort of supports that, also related to the video. Go ahead.
what if you have a function that like from 0.001 to 0.002, it goes to 1 million and comes back down.
Yeah.
Right, and you define your epsilon like 500,000.
Okay.
It only covers part of like the million that it jumps up to. Does that definition still hold? Or?
Well, I'm going to say yes because I didn't make it. You're thinking about how it would hold.
Yeah.
Well, wait, remember the epsilon though. Well, what's wrong with that though? Because if the limit is 1 million at some point in there, then we can build an epsilon that just varies off of a million a little bit. And then we would find a delta that varies off of whatever the x coordinate is a little bit.
I'm just saying like say your actual point is like this is a lot easier with high decimals. Let's just say you have the points your x values are 1, 2, and 3. At 1 it's 0. At 3 it's 1. And then somewhere between 1 and 3, let's just say 2, the function is defined at y equals a million, right? So I'm saying
At just one, like 1 point.
yeah, but it's obviously continuous and it goes
Oh,
to
it's
a million,
continuous, okay, yeah.
right? And so let's say you're trying to find the limit as you're trying to find the limit as x approaches 3. So you define your epsilon as let's say 0.5.
Yeah.
Right? And that 0.5 would be you go 3 below. Let's say f of 3 we said it was 1. Right?
Yeah.
So you would go down to 0.5 up to 1.5. That doesn't include the range that doesn't include f of 2, which we said is a million.
If you picked epsilon to be 0.5, wouldn't you be looking within the neighborhood of 2.5 to 3.5? Yeah, because
okay, no, that makes sense.
yeah,
'Cause then if you define your epsilon to be a million, then you would be looking in the neighborhood from 0 to 1.
Yeah. If your epsilon is a million, then if you're looking at what happens at 3, then whatever f of 3 is or is not, but maybe there's a limit there, right? Then the million goes from that value
Right.
down and up that much,
Okay.
right? But epsilon's supposed to be small, so I don't know if a million would be a good thing. But anyway, okay, so that's the formal definition. And then there's 3 other ways that I saw in our text that I wanted to make you aware of, okay? So other ways to say this, other ways to understand what this is saying, okay? So the limit, all that stuff, the limit is L. This means that the distance between f of x and L can be made arbitrarily small by making the distance from x to a sufficiently small. I liked each of these for the kind of in their own way, and I will cite my source here. I'm taking this straight out of our textbook. If you read that again, so the limit means that the distance between f of x and L, remember L is the proposed limit, can be made arbitrarily small. That's the epsilon, right? That distance is the epsilon, by making the distance from x to a sufficiently small. And that sufficiently depends on the arbitrary, right? Depends on the epsilon. Okay.
So that's how you account for if it jumps up to a million, you just make it smaller.
Yeah. Okay, so the second explanation, they're all, of course, very related, but this one says the limit of f of x being L means that the values of f of x can be made as close as we want to L. So the values of f of x can be made as close as we want to L by making x, how should we state this? I don't like the way the book says it necessarily. By taking x close enough to a, why don't we say by making x, say,
Sufficiently.
yeah, we could use that term again, I guess, but by making x, how about this? A particular closeness, a particular closeness to a. Maybe that sounds funnier than the book, but whatever, right? And then the formal statement, and I want to draw this one with a picture because I don't want to write the whole thing again. I think we have this idea of being within delta and epsilon, but I liked this. I liked the book how it showed if here is a, and this is a plus delta, and this is a minus delta. So this is my input set or my domain. When x lies in here, then that necessitates that f of x lies somewhere in there. Lies within, oh, sorry, this should be L plus epsilon and L minus epsilon. So that's really, that picture is getting at what is being said in epsilon delta proof. Now listen, I never learned this in high school. I didn't learn this until real analysis. This was my senior year of college, I think. And it confused the heck out of me until I tried to teach it, okay? And so I'm just trying to give you a little primer on it so that you've heard it once, you've maybe thought about it a little bit, maybe tried an example, so that when you encounter it in real analysis in college, it's not as confusing for you as it was for me, okay? That's my attempt. Believe me, I don't have a full orbed understanding of this, okay? I would need to study it a lot more. But let's have you try one now from scratch, okay? So prove that the limit as x goes to 3 of 4x minus 5 equals 7. Give it a try. You and your table can chat.
Real analysis required.
No.
All right. Other than this, is it a fun class?
No, it's hard. It's really hard. I mean, that doesn't mean it's not fun, but
I know, but like, is it hard fun or is it like want to rip your eyes out fun?
I don't know, actually. I don't know how. I'm not really sure. I need to go back and find my notes or something. I don't remember it well enough.
But it can't have like a. Epsilon over 2 plus 3,
What we gonna make that?
I think
I think the same out 0.1. Basically. Basically, too. You might as well just say it's that's engineering. That's called an engineering. All right, so what would we decide to make epsilon in this situation?